picture this. You're sitting in your living room. Maybe you have like a hot cup of coffee in your hands.
Oh, yeah. Sounds perfect.
Right. And you're just listening to the rain pounding against the windows. I mean, it's the absolute height of the rainy season.
Which can be so cozy.
Exactly. It feels incredibly cozy. You're inside, you're dry, and all those chaotic elements are just locked firmly outside where they belong.
Safe and sound.
Safe and sound. But what if I told you that while you're relaxing on the couch, catching up on a show, there's this invisible, completely silent threat rapidly accumulating right beneath your feet?
Oh, wow.
Yeah, a threat that is actively compromising the very foundation of your home.
It's a deeply unsettling image, honestly, once you realize what's actually happening down there.
It really is.
Because we tend to think of rain as just, water that falls from the sky, hits the grass, and eventually washes away down the street.
Just goes into the gutter.
Right. But the reality of what happens to all that water, especially the water that doesn't just wash away, is much more complicated. And frankly, it's a lot heavier.
Heaviness is the absolute perfect word for it. And that's exactly what we're getting into today. Welcome to today's deep dive, where we're taking you into the literal, murky underbelly of homeownership.
Yeah, we are definitely going underground for this one.
We really are. So we're pulling from this fascinating transcript of a video by the YouTube channel How to Plumbing. The video itself is framed as a step-by-step DIY guide.
Right.
It's about replacing a broken sump pump for a customer whose basement was, well, actively flooding.
Which is an absolute nightmare scenario.
Total nightmare. But don't worry, we're not just going to read off some boring list of hardware store instructions.
No, far from it. What we're really unpacking today is a profound case study in structural survival.
I love that phrase, structural survival.
Yeah, because it's about engineering, fluid dynamics, and human ingenuity, basically facing off against nature.
And it's also what I can only describe as an absolute masterclass in working smarter, not harder.
Completely.
We're going to explore the surprisingly elegant mechanics of how homes survive these massive storms, the incredibly high stakes of subsurface water pressure, and the brilliant shortcuts professionals use to guarantee success.
It's going to be a fun one.
Okay, let's unpack this. Because before we can even talk about how to fix a broken pump, we really have to wrap our heads around the massive invisible forces this little machine is actually fighting.
Right.
I mean, early in the video, the plumber points out that water is literally pouring in from pipes on the side of the sump pit while he's just took the work.
It's just nonstop.
Where is all that water even coming from?
Well, if we connect this to the bigger picture, that water pouring in isn't just a stray puddle from a leaky window.
No.
When it rains heavily for days, the soil surrounding your entire home becomes completely saturated.
Like a sponge.
Exactly. Think of a sponge that just cannot hold another drop. The water has nowhere else to soak in, so it pools underneath the footprint of the house itself.
Just sitting there.
Right. And this creates a terrifying physical force called hydrostatic pressure.
Hydrostatic pressure, which sounds like something out of a submarine movie.
It's very similar, actually. Imagine the sheer weight of tons and tons of water trapped in the earth.
Because water is heavy.
Incredibly heavy. A single gallon weighs over 8 pounds.
Wow.
Now imagine thousands of gallons trapped in the soil, actively pushing up against the underside of your basement floor. It basically turns the ground beneath you into a giant hydraulic press.
And the video mentions that without a working sump pump to relieve that tension, this pressure could literally crack the solid cement foundation of the house.
Just snap it.
That's terrifying. It really makes me think of your house not as a sturdy building rooted deeply in the dirt, but more like, I don't know, a hollow ship floating on a temporary, angry underground lake.
That's a really accurate way to look at it. Because concrete is a fascinating material.
Oh, so?
Well, it's incredibly strong under compression, meaning it can support the massive weight of the walls, the roof, the furniture from above without breaking a sweat.
Right. Pushing down is fine.
Exactly. But concrete is surprisingly brittle when it comes to tension, which is the upward bending force from below.
Oh, I see.
Yeah, so when that underground lake pushes up, the concrete can't bend. It just snaps. It breaks to give that pressurized water an exit route.
Okay, so to stop our concrete ship from snapping in half and sinking, homes have this unseen collection system built right into the earth.
Right, the defense mechanism.
Yeah. The plumber describes this perimeter pipe that runs all the way around the basement footprint. It's essentially a pipe full of holes surrounded by loose rocks.
Like a highly engineered funnel.
Exactly.
And the physics behind it relies entirely on water's absolute laziness.
Laziness.
Yeah, water always takes the path of least resistance. The rocks filter out the heavy mud and sediment, creating an easy, porous pathway.
Oh, that makes sense.
So instead of fighting against the dense concrete slab, the water flows happily into those perforated pipes.
Uh-huh.
From there, gravity channels it on a slight downward slope directly into the sump pit.
Which is just a designated low point. I mean, it's basically a plastic bucket buried in the floor where we actively invite all that dangerous water to gather.
Right. It's the pressure relief valve for the entire underground lake.
Which brings us back to the plumber kneeling over this pit in the basement. It's wild to think about the stakes of his job here.
Seriously.
Because while he's physically pulling out the broken pump, the water from underneath the house is just continuously rushing into the pit. The enemy is actively breaching the gates while he's trying to build the defense system.
It's a race against time.
Yeah.
And that defense system relies entirely on one specific and, frankly, completely unglamorous piece of plastic to keep from destroying itself.
Just a piece of plastic.
Yeah. Because the stakes of a cracked foundation are so high, the new pump cannot afford to fail.
Which brings us to the check valve. The plumber spends a really surprisingly long time talking about this one component.
He really emphasizes it.
He explains it's a backflow device with a little flapper door inside that only opens one way, and there's an actual arrow stamped on the outside of the pipe that absolutely has to point up toward the ceiling.
That directional arrow is critical to the pump's survival. Think about the pump's actual job.
Okay.
It has to violently push a heavy column of water vertically up a pipe, sometimes 10 or 12 feet in the air, to get it out of the house.
That's hundreds of pounds of water just hanging out in the air inside the pipe.
Exactly.
Yeah.
And when the pump shuts off, gravity instantly takes over.
Uh.
All that water still in the vertical pipe wants to crash right back down into the pit.
Oh, man.
So the check valve acts as the gatekeeper. The weight of the falling water slams that little plastic flapper shut, holding the entire vertical column of water in place, suspended above the pit.
And if it doesn't snap shut, I mean, the plumber notes that if that water crashes back down into the pit, it raises the water level again, which triggers the pump to turn back on, which pumps the exact same water up the pipe, only for it to fall back down again.
It creates a catastrophic loop.
Just pumping the same water.
Yeah, the pump will just run constantly, fighting the same 10 gallons of water over and over again. It's overworking its motor until it literally burns itself out prematurely.
The video also gets into the specific sizes. It uses a 1.5-inch PVC female adapter.
Right.
And the plumber specifically shows how he removes these little rubber inserts that are meant for smaller 1.25-inch pipes.
He wants maximum flow.
Yeah, he does this to make sure the flow is perfectly unrestricted. It's just a brilliant, purely mechanical solution.
It really is.
There are no sensors, no fancy electronics to short out in the water, just a simple plastic flap governed by water pressure.
It's the unsung hero of the entire operation.
Okay, but I have to stop you there and push back on something the plumber did because it drove me a little crazy.
What was that?
He reaches his hand into this submerged, dirty pit and pulls out the old check valve. He wipes it off, and he actually admits on camera that the old valve is still in pretty good shape.
Oh, yeah, I remember that.
He says it's just a bit older. So why spend the time, the effort, and the customer's money replacing a perfectly good part?
It's a fair question.
Isn't it easier and frankly cheaper to just swap the broken pump, screw it into the existing pipe, and be done with it?
It is so tempting to think that way, especially if you're tackling this as like a weekend DIY project and you're tired, you're muddy, and you just want the flooding to stop.
Exactly. Just plug it in and go upstairs.
But the plumber's logic here is deeply rooted in the philosophy of preventative maintenance. He uses a very specific, deliberate phrase in the video.
Oh, right.
He says he wants the new check valve to age together with the brand new sump pump.
Age together, like they're a married couple.
Well, I'd compare it more to the tires on your car. If you're driving on the highway and you have a blowout on your front right tire, you could technically just drive to the shop and replace that one ruined tire.
It's cheaper.
Right. But your car is going to drive terribly.
And more importantly, you're leaving yourself dangerously vulnerable.
How so?
If the other 3 tires already have 50,000 miles of wear and tear on them, another blowout is imminent.
Ah, I see.
In a mechanical system designed to prevent catastrophic flooding, an old check valve is a ticking clock. The plastic flap gets brittle over years of slamming shut. The hinge wears down. The rubber seals degrade.
It's just bound to break eventually.
Exactly. By letting a brand new valve and a brand new pump age together, the plumber is intentionally resetting the lifespan of the entire system to 0.
Oh, I see. He's refusing to let a $20 piece of old plastic jeopardize his $300 pump,
Yes.
and by extension, a $30,000 foundation repair. He's eliminating a future point of failure before it even exists. It's the wisdom of a professional looking at the system as a complete ecosystem, rather than just treating the immediate symptom, which is the broken pump.
That makes a lot of sense. And understanding how these interconnected parts age together really sets the perfect stage for the actual physical replacement process.
The fun part.
Right, because watching this video, the physical installation is where the plumber reveals this absolute masterclass in DIY efficiency.
Oh, it's so satisfying to watch.
I am notoriously terrible at home repairs. Every project involves 3 trips to the hardware store and endless frustration.
That's par for the course for most of us.
But here's where it gets really interesting. His whole process is aggressively designed to minimize human error.
The methodology he uses is arguably more valuable to a listener than the mechanical steps themselves. It's a masterclass in reducing friction.
Take the pump selection itself. He doesn't go to the hardware store and buy the newest, flashiest model with Bluetooth alerts and laser sensors.
Keeping it simple.
He goes out and buys the exact same brand, a little giant pump that was already sitting broken in the pit. By getting the exact same model, he says he avoids any piping modifications. The connections match up perfectly.
What's fascinating here is how his approach to problem solving is entirely focused on removing variables.
Variables, right?
In plumbing, every modification you make, adding a new adapter here, introducing a slight bend in the pipe there because the new pump is 2 inches taller, introduces a new variable.
And a variable is just a leak waiting to happen.
Exactly.
And he takes that remove the variables mindset to a level I absolutely love.
The measuring.
Yes. When it comes time to cut the new PVC pipe to connect the pump to the house's exit line, he doesn't reach for his trusty measuring tape.
He doesn't even look at one.
He says it right in the video.
Yeah.
Rather than pull out my trusty measuring tape, I'm just going to line them up side by side and cut it to the exact same thing.
It's so elegantly simple, but it completely bypasses the most common source of DIY failure.
It totally does. It reminds me of getting a spare key made at the local hardware store.
Oh, that's a good analogy.
Right. Because the employee doesn't take out a tiny ruler, meticulously measure the angle and depth of every single jagged tooth on your house key, and then try to mathematically recreate those measurements on a blank piece of metal.
That would take forever.
And it would be completely absurd. The math would invite so many mistakes. Instead, they just clamp the old key and the new key side by side in a machine and physically trace the shape.
Tracing reality bypasses the math.
And bypassing the math bypasses human error entirely.
Yeah, translating a physical object, like a pipe, into abstract numbers on a tape measure, and then translating those numbers back into a physical mark on a new pipe.
There's too much room for mistakes.
That translation process is exactly where mistakes happen. You read 16 3/4 in the dark basement, but you mark 16 5/8.
And you're ruined.
Suddenly, your pipe is too short, the joint is stressed, and the system fails.
Mm-hmm.
By laying the old assembly and the new PVC side by side on the floor, he ensures absolute fidelity to the original working design.
And he doesn't stop there with the specialized tricks to protect himself from mistakes.
Oh, the seesaw.
Yes. When he makes that side-by-side cut, he explicitly points out that he's using a specialized PVC saw, not a standard metal hacksaw that most of us have rusting in a toolbox.
Right.
He notes that it is really hard to keep a thin hacksaw blade straight, but the PVC saw is thicker and designed to keep the cut perfectly flat.
Which is absolutely vital when you're dealing with PVC cement. You know how that glue smells incredibly strong?
Oh yeah, it's overpowering.
That's because it's not actually glue.
Wait, really?
Yeah, it's a chemical solvent. It temporarily melts the outer layer of the plastic pipe and the inner layer of the fitting.
Oh, it actually melts it.
Actually melts it. When you push them together, they fuse into one solid piece of plastic. It's a chemical weld.
Oh.
But that weld only works if the surfaces are in full, flush contact. A crooked, wobbly cut from a hacksaw means the pipe won't seat fully inside the fitting. You'll have gaps.
And gaps mean leaks.
Right. That creates a weak joint, which, under the violent pressure of a sump pump kicking on and off hundreds of times a day, will eventually blow apart.
So again, he's removing the variable of a wobbly human hand from the chemistry equation.
Exactly.
That makes total sense. And he even brings that ruthless efficiency to the hand tools he uses. He pulls out this six-function multi-screwdriver to tighten the metal bands on the rubber couplings that hold the pipes together.
Yeah, the rubber couplings.
But he doesn't use the Phillips or the flathead bits. He pulls the bits out entirely and uses the hollow metal shaft of the screwdriver strictly as a socket wrench to tighten the hex nuts on the bands.
It's the hallmark of someone who has spent way too many hours in dark, wet basements.
Seriously.
Finding multiple uses for a single tool saves time, sure. But more importantly, it ensures a tight, secure grip.
Because flatheads always slip.
If you use a flathead screwdriver on those metal bands, it definitely slips. And if it slips, you might drop the tool, or worse, drop the tiny metal screw into a 2-foot-deep pit of black, murky water.
Oh, that would be the end of my day right there.
Right.
Yeah.
But using the hollow shaft as a socket captures the nut completely.
Okay, so let's look at what he's built. He has meticulously measured his pipes without actually measuring anything.
Yep.
He's made perfectly flat cuts for strong chemical welds, and he's got the identical new pump and the new upward-facing check valve firmly attached.
All set.
He has basically built this pristine, error-free mechanical assembly right on the dry basement floor. Now it's time to actually put it into the danger zone.
The pit.
The pit. And the final installation steps reveal the true automated elegance of the completed system.
It all comes together at the bottom of the pit. Literally.
Right, because at the beginning of the video, the plumber noticed some old, grimy bricks sitting at the very bottom of the sump pit. They were completely submerged under the water. And instead of tossing them out with the broken pump, he specifically places those slimy bricks back down there to support the new pump.
It seems counterintuitive.
It does. Why use old bricks? Why not just sit the pump directly on the flat bottom of the plastic pit? It seems like it would be more stable.
It's actually a crucial detail for fluid dynamics.
Fluid dynamics again, okay.
Sitting the pump directly flush on the floor of the pit can choke its intake. The bricks elevate the pump just a few inches, creating a physical gap underneath the unit. This allows the water to flow freely from all sides under the pump and be efficiently sucked up into the bottom intake grate.
Like putting a vacuum cleaner nozzle perfectly flat against a rug versus hovering it slightly above.
Exactly. If it's flat, it creates a seal and starves the motor. Furthermore, those bricks keep the pump slightly elevated above the absolute bottom layer of the pit.
To keep it out of the muck.
Yes. Over time, silt, mud, and gravel inevitably wash through those perimeter pipes and settle at the bottom. By raising the pump, he's preventing the mechanical spinning impeller from sucking up rocks and getting jammed.
So even the random bricks in the mud are a calculated part of the defense system.
Every single detail matters.
But here is the moment in the video that genuinely made me pause and realize the brilliance of the design.
The drop-in.
Yes. So what does this all mean? We have a pristine pump, and we have a pit currently full of dirty, gross water that's been actively backing up into this person's basement.
It's pretty nasty.
I'm watching this thinking, okay, time for the miserable part. Time to get the loud, wet vac. Time to get a 5-gallon bucket. Let's bail this nasty water out by hand before we put the shiny new equipment in.
That's what most people would do.
But the plumber just completely skips the grueling cleanup step entirely.
He trusts his assembly. And more importantly, he trusts the mechanics of the machine.
He literally just takes this brand new, perfectly assembled pump, drops it straight into the flooded, dirty water, and plugs it into the wall.
Plugs it right in.
He just lets the water sit there because he knows the machine will handle the cleanup for him.
That's the beauty of the automated depth trigger, often called a float switch.
A float switch.
It's essentially a hollow plastic bulb floating on the water tethered to the pump. Inside that bulb is a heavy metal ball.
Okay.
When the water level rises, the bulb floats upward, tilting until the metal ball rolls to the bottom and completes an electrical circuit, turning the pump on.
That is so simple.
It is. This pump doesn't just run blindly. By dropping it into a pit that is already flooded, he is instantly floating that switch and triggering the circuit.
And it triggers immediately. You literally see the water start churning, and the little giant pump just aggressively sucks it all up, pushes it through the new check valve, up the straight PVC pipe, and blasts it out to the storm drain ditch outside.
It's amazing to watch.
The system essentially cleans up its own mess the very second it is given electrical power. Our concrete ship's bilge pump is officially back online.
It's a highly satisfying mechanical conclusion. It proves in real time that the entire loop is functioning exactly as designed.
All the parts working together.
The subsurface pressure pushes water to the perimeter pipes, the pipes funnel it to the pit, the rising water triggers the float switch, the pump evacuates the water, the check valve holds the line, and the foundation is kept entirely safe.
It really is deeply satisfying to watch everything click into place like that. Let's do a quick recap of this journey for you, the listener, because we have covered a massive amount of ground today.
Literally.
Literally. We started by picturing the terrifying, heavy physics of an underground lake exerting hydrostatic pressure, threatening to crack your cement foundation.
Which is something you never want to see.
Never! We walked through how a seemingly simple perimeter pipe uses water's own laziness to funnel that threat into a single pit.
Water is lazy.
We watched a professional bypass human math errors by tracing pipes side by side like a house key. We learned the surprisingly violent physics of why a $20 check valve must always point up,
That's critical.
and why it has to age together with the main pump like a set of car tires. And we ended with a little giant pump resting on a few humble bricks, instantly clearing a flooded pit all by itself.
It's a remarkable, reliable sequence of mechanics that protects millions of homes. But this raises an important question, one that goes beyond just the satisfaction of DIY plumbing.
Oh, I like where this is going. What's the question?
Well, the video ends with the plumber proudly saying, "Hey, your work is done," as the pump lowers the water level until the float switch drops and shuts the motor off.
Right, the ball drops down, breaks the circuit.
Exactly, it feels like a victory. But if you look closely at the footage in those final frames, even as the pump turns off and the pit is mostly empty, water is still visibly pouring into the pit from those side perimeter pipes.
Still pouring in.
The rain outside hasn't stopped. The massive hydrostatic pressure hasn't magically disappeared,
Oh, wow, you're right. The water just keeps coming.
which means the battle against nature under your home is never actually won. There is no final victory lap. It is a perpetual, invisible standoff.
A standoff.
Right now, and every single time it rains, that hidden machine and its simple plastic flapper are locked in an endless, grueling cycle. The pit fills, the switch triggers, the pump evacuates, the valve slams shut, and it resets
Wow.
over and over and over again. It's fighting the rising tides continuously, completely automatically, keeping your foundation from cracking in half while you sleep safely upstairs.
That is a lingering, slightly awe-inspiring image to leave on. A silent mechanical sentinel in the dark basement holding back the underground ocean. Next time you're sitting on the couch with that cup of coffee, listening to the rain tapping on the glass, maybe take a second to appreciate the quiet, relentless war being fought and won right beneath your feet.